The following video lesson comes from Flip for Math, iPad's premier interactive Common Core toolbox. Flip for Math is now available on the iBook store for under $2. What do you think is wrong with the following animations? Would you have expected them to look more like this? The reason that the first set of animations looked wrong is because we used the wrong function to represent the true behavior in these situations. A falling egg accelerates due to the force of gravity. Each cell continues to divide into two identical cells in the process known as mitosis. And the price per gallon of gas should be consistent, until tomorrow, that is. All three of these scenarios require different types of functions. To better understand the difference between the various functions, let's compare them in a story dealing with spreading rumors at school. Two people at school like to spread ridiculous rumors about their classmates. However, each person has their own style of spreading rumors. Jeff tells 5 new people every day, but only after he swears them to secrecy. Megan tells 2 people the first day and then has them tell 2 new people the next day. Everyone who hears the rumor is obligated to tell 2 new people. Let's look at a table to see how many new people have heard each rumor after a few days have passed. By the end of school on Monday, Jeff's rumor has reached 5 new people, and Megan's rumor has been heard by 2 new people. Whose rumor do you think will reach more people by the end of the school week? How about after the weekend? After 3 days, Jeff's plan has worked better, but after a full week, Megan's plan has reached many more people. Assuming these patterns continue, how many people will have heard the rumor after 2 full weeks? It looks like Jeff needs to step up his game. Let's look at how many people will have heard these rumors after an entire year. After 365 days, Jeff's rumor will have only reached 1,825 people. Megan's rumor, on the other hand, will have reached such a large number of people that the number representing them would be 110 digits long. Unbelievable. In fact, with an estimated 7 billion people on the planet, the entire population of the world would have heard Megan's rumor by the 32nd day. Now let's go back to our original table. How would you describe the pattern of growth you observe within each column? What's happening as you move from one row to the next? You probably mentioned that Jeff's rumor reaches 5 new people each day over the previous number. With Megan's rumor, the number of gossipers doubles each day. This leads us to a must-know fact about patterns of growth. The process of doubling always outgrows the process of addition. Always, you ask? So here's an absurd scenario to illustrate this fact. You win a lottery and are given a choice about what your prize will be. You can either receive $200 per minute for an entire day, or you can receive $1 on the first minute with a 1.02% increase each additional minute. Which do you choose? The function r adds $200 to the previous number, and s multiplies the previous number by 1.02. Surely, there is no way that s will ever beat r, right? Be careful, look what happens as x gets just a little larger. It took a while longer, but somewhere between 500 and 600 minutes, the s function wins. Now, let's plot these functions on a graph. Just like we saw in the table, function R starts out big and grows steadily at $200 per minute. Function S, on the other hand, grows proportionally to its current value. When the value is small, the growth is small. However, as the value becomes larger, the growth remains proportional to that larger quantity, and then suddenly, bam! Rapid growth is taking place, dwarfing the function that adds $200 per hour. Functions that grow by the process of addition, like Jeff's rumor, the $200 per minute lottery prize, show equal and consistent growth. Functions that grow by the process of multiplication, such as Megan's rumor or the lottery prize that increases by a minuscule 2% per minute, show accelerating growth. Remember, the accelerating growth always surpasses the steady growth. In this lottery example, we compared two functions, each represented as tables and then as graphs. But sometimes we have to compare the properties of two functions that are represented in different ways. Perhaps one is a table and the other is a graph. Imagine you are the lead engineer for a car company. You and your team are working to design a car with the best fuel efficiency. Fuel efficiency, often referred to as gas mileage, is a function of many variables, but one of the independent variables is the speed at which you're driving. We could say that G equals F of S, where S is your speed in miles per hour and G is the fuel efficiency in miles per gallon. The function f relates these input and output values. One day, two of your top engineers working on two different engines bring you some data to compare. Amy represents her data in a table, and Brad represents his data in a graph. They present the following fuel efficiency data. Which vehicle is capable of the best gas mileage when driven at the right speed? Amy's car can achieve 32 miles per gallon, but Brad's can only get 25 miles per gallon. At what speed are each of these cars most fuel efficient? Looking carefully at the input values, Amy's gas mileage is maximized when it's traveling at 40 miles per hour. From the graph Brad provided, his car is most efficient at 50 miles per hour. Now, let's compare two functions where one is presented symbolically and the other as a graph. Will we still be able to interpret key features? The dollar value of a new 2012 Toyota Camry can be modeled by the function v of t equals 26,000 minus 2100 t, where t is the age of the vehicle in years. Compare that to the graph of the value of a new 2012 Honda Civic. Which function's graph has the higher vertical intercept? What does that mean in terms of the value of these cars? The Honda Civic graph intersects the vertical axis at 22,000, but the Toyota Camry's function has a vertical intercept of 26,000. How do we know? The vertical intercept can always be found by plugging in 0 for the independent variable. So, what do these numbers mean? They are the values in dollars of each vehicle when they are 0 years old. Brand spanking new. Okay, all of this math is making you hungry. You decide to get a Big Brute's pizza. The total cost, C, in dollars of a large pizza with T toppings is represented by the function C of T equals 1.5T plus $8.99. Let's interpret the numbers found in this function. What does the $8.99 mean in terms of a pizza? How about the 1.5? Notice that our cost is $8.99 if we add 0 toppings. So this is the base cost for a cheese pizza. So what does the 1.5 represent? You got it, it's the price per topping, $1.50. Let's have a quick review. Different situations require different types of functions. A quantity that grows by multiplying will always outgrow a quantity that grows by addition. And finally, functions can be represented verbally, symbolically, numerically, and/or graphically. Important properties can be found in any of these representations.